Okay, so today we have Fernando Flor, and he's giving a talk on flavor, energy, and system size dependence of the chemical freeze-out and relativistic particle collisions from RHIC-BES to LHC energies via statistical hadronization. Fernando did his undergrad at the University of Texas, Rio Grande Valley. He is currently a graduate student at the University of Houston working on the ALICE collaboration. In addition to analysis, Fernando has worked on genutectors for the TPC upgrade for the ALICE experiment and is involved in many DEI activities, including being a junior representative for ALICE, a member of the ALICE Diversity Office, and also a junior graduate student representative at Houston. And then most recently, Fernando was awarded a Fulbright, and he will actually be joining Yale as a postdoc in the winter, while he will continue to research with the ALICE collaboration in the heavy ion group here, and also pursue DEI projects. And so, Fernando, if you are ready, you can go ahead and start.
Awesome. Well, thank you very much for the introduction. Also, thank you very much for having me here. I'm very excited to be here today, and I'm obviously also very excited to join the group for our future endeavors together. So I guess it's already been introduced that I'm going to give this talk on flavor, energy, and system size dependence of the chemical freeze-out for relativistic particle collisions through statistical hadronization. Once again, I'm Fernando Flor, I'm a graduate student in the University of Houston, working under Professor Yale Wright. So I'm just going to go ahead and get started because I don't want to run out of time, and there's some things that I want to get through. But overall, the talk will be split into three parts. In the first part, I'm going to be focusing on collision energy dependence of chemical freeze-out, particularly going from star energies all the way up to LHC energies. And then from the results gained from that, I will move specifically into at least system size dependence for all three systems that we have. And the latter parts, I'm going to talk about some modifications that we've been working on currently in Strasbourg for the hadronic spectrum, particularly expanding it onto the charm sector. So for energy dependence, I think a good place to start will be talking about extrapolated lattice QCD results from the chiral susceptibilities that we see from both the light and the strange quarks. And what we do see here on the plot on the left is that there is different behaviors between light and strange quarks, seen in red and blue respectively, where we also see some flavor-specific kinks at specific temperatures. Now, it does so happen that these deviations of the lattice curves coincide with these kinks that we're talking about. And there is about a difference of 15 mega electron volts between the light and the strange flavors. Moreover, there have been similar findings existing within the HRG resonance gas model calculations from event by event net particle multiplicity fluctuations, chi1 over chi2 ratios, as well as from thermal fits based on experimental yields, which we actually see here as evidence from STAR. So on the left, what we see are actual separation of temperatures based on different particle fits onto a thermal model, in which we do see an increase in the temperature as more and more particles are actually included into the fit. Now, it's not just specifically more and more particles, but it does turn out that the particles that are being included into the fit turn out to be strange hadrons. So this is already somewhat of a suggestion that it might be that this chemical freeze-out temperature might be different as we start adding more and more strange particles into the fit. Additionally, based on fluctuations, we do see once again about a 15 to 20 mega electron volt difference based on these flavor-specific chi1 over chi2 ratios. So this is at STAR somewhat of an evidence supporting an energy-dependent separation of freeze-out temperature. And lastly, of course, at least we also not so apparently see this separation of chemical freeze-out temperature, but what we do see from the thermal fit models that we have, typically describing the data at least, is that although there is an overall chemical freeze-out temperature that sits at around 156 MeV, which coincides with the pseudo-critical temperature from lattice QCD and performs an overall good fit of the data, what we do see once we look at the lowermost panel is that there is an apparent tension between strange and light baryons. Namely, there's going to be about a 5 sigma difference between, say, the protons and the xi's. So although it might be an overall good fit into the thermal model, once we start looking into particle-specific fits and the particle-specific sigmas, we do see that overall the fit with respect to flavors may not all be too good. So the question that we actually have to ask ourselves, or that I've asked myself for my dissertation topic, is whether or not hadronization will occur at the same temperature for all quark flavors. And this is where we move into this, what we call the two chemical freeze-out approach. So with respect to sequential strangeness freeze-out in this two chemical freeze-out approach, what we do is we entertain the idea of two chemical freeze-out temperatures, namely such that the strangeness freeze-out temperature occurs prior to the light freeze-out temperature. Now, in the typical space-time diagram that we're all used to, this would pertain to an earlier freeze-out, which corresponds to a higher temperature prior to the light flavor freeze-out temperature. And what we can actually do based on statistical hadronization is make it such that we start performing flavor-specific fits to see whether or not the 2CFO approach produces a more natural explanation for strangeness enhancement across various systems, across various system energies, and also whether or not the data itself can be explained in a more natural fashion. And this is where we basically get started with the analysis. So for the actual tool that is used in the analysis, is specifically going to be using the Thermal-FIST, which is a user-friendly package which is within the family of hadron resonance gas models, and provides a huge array of different type of HRG model options that we can use. But specifically for the energy dependence part of the analysis, what I did was stuck to the ideal hadron resonance gas model, and specifically stuck with a Grand Canonical ensemble, specifically when dealing with these heavy ion collisions. So from this, what we do have additionally, other than being able to perform thermal fits, we can have a thermal model mode, which we can use from the thermal fits to calculate yields from the fixed freeze-out parameters. And this is something that I'll focus on in the second part of the talk. The event generator mode with respect to this analysis is not used particularly, but it can also be used to implement other analyses, specifically for fluctuations, which are also of utmost interest. So one thing that the user does have a huge amount of freedom with is both the hadronic spectrum that go into the model that is being used, as well as the experimental yields. And I did just want to cover these a little bit because it turns out that these are actually going to be the anchor to the results that we were able to produce. Now, first of all, as to what is the hadronic spectrum, well, the hadronic spectrum itself will be derived specifically from the particle data booklet or the particle data group list. So just to make things a little bit more simple, an ideal HRG model will be assuming a non-interacting gas of hadrons and resonances. And it turns out that the more complete the hadronic spectrum is, the closer the model will be to reality. And when I say complete, I do mean that the more that the actual decay channel information, as well as branching ratios, and obviously also particle masses and widths and threshold values, will obviously be, the more that you have them closer to what has been seen in the PDG, the better the results are going to be when performing fits. So there are different levels of confidence in the existence of individual resonances in the PDG, where the 4-star states are going to be denoting well-established states, while the 1-star states will be denoting those that basically are lacking decay channel information or branching ratio. And for us in this analysis, the hadronic spectrum at hand that we're going to be using is this PDG 2016 plus list. So it was derived specifically from the 2016 PDG with an additional number of hadronic resonance, particularly for cascades. And it will be including the 1, 2, 3, and 4-star states. In total, having an amount of 738 states into it. It has been shown in this nice paper by Alba et al. That it is this specific list that provides the best compromise between having too few states, such as that in the PDG 2016 list, and too many states, which is what is determined by theoretical quark model calculation. So basically a quark model calculation for these states will just have the total possible number of states, but it's not always going to be the case that these are experimentally verified. And if you want to see a detailed description of the difference of the list into the fit, you're more than welcome to click on this link whenever you have some free time. Now, that was the first part of what the user has basically freedom with. And for the experiment, I'm sorry, for the experimental yields that we use for this energy dependence portion of the analysis, we're going to be working with ALICE data in lead at 2.76 TeV and at 502 TeV in the most central bins. Now for STAR, what we will be using as well will be the 200 GeV data all the way down to the 11.5 GeV data. Now it does turn out that for these STAR energies, the antiproton yields themselves, as they are declared on the papers, they're actually gonna be all inclusive with respect to the weak decay feed down contributions from the lambdas. So for this work, what we went ahead and did an extrapolation from Anton's paper in order to correct the proton yields. And then from that, we were able to just use those into the fits in order to just basically have a nice little conservative estimate for these values. And I think I'm just gonna basically jump into what the procedure will be. So the procedure is as follows. We use the input available from ALICE and STAR data, and we plug it into the FIST in order to extract the freeze-out parameters. Once again, we're going to be using this Grand Canonical ensemble and focusing also, like I said, in 0 to 10% centrality. The model will be ideal, and the fit parameters in the model are going to be the freeze-out temperature T and the volume B, as well as mu B. Mu B is not going to be fixed specific values because since we do have a wide range of energy, it's not going to be the same and it will be varying with respect to system energy. And what is then done into the particle fit is basically introduce the entire zoo of charged particles that we do have. And then we start playing this game that was shown in the fits that were performed by STAR in which we actually vary the particles that are going to be going into the fit. But rather than doing one particle at a time, we'll just be focusing on the light flavor particles and the strange flavor particles, and then actually seeing how that differs from having a full fit. And then from that, we can compare that to the lattice and see if our findings fall within the actual bands that are drawn in by the lattice. So I'm just gonna talk about basically the particles that we're all sort of very familiar with. And what we do want to see here is basically not just the change in mass between the particles that we're having into the fit, which are clearly very important in the hadronic spectrum as well and as the HRG, but also how it is that the absolute strangeness value for all of these is changing. And this is also something that is very important when considering these changes into the particles into the fit. But however, for us, we're just going to basically see what the difference is between having the absolute S particles into one fit and then throwing the rest into a separate fit and then seeing if we can actually extract the difference in freeze-out temperature that will match this 10 to 15 mega electron volt difference that has been shown from the theoretical calculations. So this is an example of what a fit will look like. This fit is specifically going to be for lead-lead collisions at 502 TeV at ALICE. And what we see here is basically at the top is just going to be what the yields are, experimentally shown in green, and then what the actual calculated values are through the model. Now there's going to be two bands, one in magenta and another band in blue. And the difference between these two bands will specifically be showing you what it is that the model calculates once we let the actual temperatures be determined by only fitting specific particles into the fit. Now the actual particles going into the fit for the magenta bands will be basically everything that you see listed here. And then for the blue bands in this 2CFO approach, we have a T sub L temperature that was calculated, to be 142 MeV. And that is the temperature that we extract when we fit the pions, the kaons, and the protons into the fit. And then what we also see is a different temperature, which we have as T sub S, which falls at around 164 MeV, which will be the temperature that was extracted by fitting the kaons, lambdas, psis, omegas, and the phi into the fit. And what we can see at the bottom is basically you're going to see how the model with respect to the data performs with also respect to the actual sigmas themselves of the data. And overall, what we do see in the lower hand plot is that the blue bands seem to perform probably most of the time better than the magenta bands, at least in the lead 502 data. So this procedure that we have here was actually performed multiple times, not just the DLE's data, but across the entire beam energy scan. And what I went ahead and did after that was basically plot the extracted temperatures for all the energies into a single plot in which we compare the freeze-out temperature, which we see in this plot here in the y-axis, versus the baryo-chemical potential that is calculated by the thermal model. So in this plot here, what we see is basically the pi kp lambda psi omega k05 fit, which is basically fitting all the particles into the fit. We went ahead and plot them for all the energies that we have available. And then what we did was perform a spline fit with 3 anchors to be able to extract a vanishing baryo-chemical potential, a freeze-out temperature, assuming that there will only be 1. And we get a value of about 157 mega electron volts. So the next question that we have to ask ourselves is, okay, well, how is this procedure going to be different if we do the same spline fit, but only onto the flavor-specific fits? And the flavor-specific fits onto the spline fits look like this in the following. So once again, we have the freeze-out temperature on the y-axis and the baryo-chemical potential in the x-axis. However, this time around, we have 2 flavor-specific fits in which the blue represents the strange flavor fit for the systems that we have in the actual fits themselves. And then we have a red fit, which will be for the pi kp fit, which we're calling the light flavor freeze-out. Once again, we perform 2 separate spline fits. And then what we were able to do is extract a freeze-out temperature at vanishing baryo-chemical potential, from which we get a temperature for the light flavor freeze-out of 150 mega electron volts, which is shown here in red. And then we get a strange flavor freeze-out of 165 mega electron volts. And what we went ahead and did as well was plot this with respect to the freeze-out temperature that is calculated by lattice QCD. And it does seem that our calculations for both of these curves fall within the calculated sigma values that are determined by the lattice QCD calculation. So it pretty much tells us that within this crossover region that is of concern for all of us, it does seem that these results might not be too far-fetched, assuming that there is a mixed phase in between the actual values. Now, one observation that we do see here is that by eye, we can tell that both the T sub L and the T sub S lines converge somewhere up here at high mu V. So we can make the pretty bold claim that if we use these temperatures that we extract from yields, which themselves serve as susceptibility proxies, then our measurements may or may not signal the existence of a critical point existing at high mu B. But it is far outside the reach of the extracted values. And the last thing that we went ahead and did in order to perform just a cross-check is to make sure that our extracted values of the 2 chemical freeze-out parameters do lie within the isentropic trajectories in the T mu B plane. These were calculated by lattice QCD equation of state that was provided by the theory group in the University of Houston, for which, as of now, the validity is to finite densities that has been shown up to a ratio of mu B to T being equal to 2. So we did have to exclude the starry gold 11 GeV values, which would sit somewhere around here. And of course, obviously the Elise lead, because we do have a divergence of the entropy per net barium. So it does seem that at least as a good cross check, it does tell us that for all energies, our lightest range of freeze-out parameters do lie well within the projected trajectories. So it does tell us that once again, the results are not entirely too far-fetched. And this basically just lets us get to the end of the energy dependence, but the message that we do want just basically to stick are these 2 specific temperatures that we were able to determine which we will now use for the system size dependence, which depends only on the Elise data for PbP-lead and lead-lead at the LHC energies.
So can I ask a question here before we go to the part? So, I don't really understand this. So why is there a negative slope as a function of mu b in the first place? Or why do you expect a negative slope as a function of mu b?
So based on intuition or based on results that we have from the lattice?
I want your intuition first, and then I want the results next.
Okay, so I mean, I would expect it to be a downward slope because at some point we do know that we have to reach this point for nuclear matter from which the actual curve itself must have a negative slope. I mean, that doesn't necessarily tell me that there's going to be a curvature to it, but I mean, it does tell you that at some point this curve needs to drop down. I don't know if that's a good answer to your question. And then I guess the latter part, why it has a curvature, I mean, the curvature has been shown to be, although very small, it does have a negative curvature with respect to the lattice QCD.
Okay, well, I guess I just need to see this in my head.
Yeah, no, I mean, I think like a majority of the time, this is something that's taken prima facie because we do see the QCD phase diagram often, and this downward slope is always shown, but actually asking us to why we would think that this is expected, it's not at all quite clear just from looking at the cartoon that is often shown.
Sure.
Okay, so yeah, so now I'm gonna basically just talk about the procedure used in the different systems that we have at Elise. So this time what we're going to do is run the FIST in thermal model mode to be able to extract the least the least yield for all three systems. And we're not just going to solely focus on one multiplicity class or I guess centrality, but since we're dealing with smaller systems, I'll refer to them as multiplicity classes from now on. And this time around, there will be a difference in the ensemble that we're using, which will be the strangeness canonical ensemble rather than the Grand Canonical ensemble. And I'll show the reason why this was done in the next couple of slides. But just to emphasize the difference between the two ensembles is that in the Grand Canonical ensemble, we have a global conservation of the usual three charges, which will be your electric charge, your baryon number, and then also as well as the strangeness conflict. And since we are going to be dealing specifically with the least energies, this allows us to make a, the big assumption that mu b is going to be 0 or close to 0. I mean, these calculations were performed multiple times, setting mu b to 0, setting mu b to 1. And with respect to the thermal model, the difference in the yields wasn't that large. So we just went ahead and fixed it to 0. And there will be two additional parameters that come about from the strangeness canonical ensemble, which will be this V sub C parameter as well as the gamma sub S. The V sub C parameter is going to be a correlation volume. And this correlation volume is going to be what exactly pertains to the difference in the two ensembles, namely that this is the volume into which now strangeness is conserved explicitly. However, we're not letting V sub C vary, we're setting it to V, which in this case corresponds to the fireball volume per unit rapidity that is calculated by the thermal model. This additional gamma sub S parameter is set to 1, which can also be set free, but for our analysis, we were assuming that strangeness is fully saturated at LHC energies, and this is also going to be a fundamental assumption in our analysis. So then the next thing that we wanted to see was how it would be that the yields themselves are basically going to be responding to fixing the freeze-out temperatures to the values that we extracted from the energy dependence procedure. So basically we're going to use, in principle, we use 3 temperatures, but the middle temperature, which we just call TCH, was only done to be able to just check what the values would look like if we assume one single freeze-out temperature. But for the two temperature approach, we're going to be using T sub L and T sub S, once again at 150 mega electron volts. For the former, and for the latter, we're going to have it at 165 MeV. The same particle decay list is going to be used. And then what we want to do in principle is plot these as they have been shown before by the ELISE collaboration. And what we're going to do is basically show an antihadron to pi plus calculated yield ratio. And I don't think that the final result was normalizing with respect to the high multiplicity PP limit, but this can also be done. I don't think I included it in this presentation, but I do have it somewhere in a file if you'd want to see that. So, I mean, the culprits are going to be identical to the previous procedure. So this should not be too different as to what's going into the fits. And this is basically the first result. And this is what I was basically talking about or referring to in the actual procedure, where I wanted to emphasize why it would be that the Grand Canonical ensemble itself fails to represent appropriately the data at ELISE. So what I'm actually showing here is the system size dependence by looking across all three systems, into which we have a Grand Canonical ensemble, and we do not fix the chemical freeze-out temperature to any value. So this was just done to be able to gauge the goodness of the fit with respect to basically just a blind fit without actually assuming there to be fixed temperatures. The only thing that we actually went ahead and did was once again vary the temperatures in the fit. So what we have in the plot is basically going to be once again in the y-axis, we have the extracted chemical freeze-out temperature, but this time in the x-axis, what we have is basically an increasing dNCH theta, which is the charged particle multiplicity density, which increases, as we know, as a function of increases as a function of multiplicity, of course, where centrality classes from smaller systems to upper systems. Now the colors here represent the three different fits that we perform. We reserve the blue and the red, once again, for the strange fit for the blue, and for the light fit in the PkP fit. And this time around, the green fit just basically corresponds to the entire SU being fit. And we want to compare how it is that the actual goodness of the fit changes with respect to these three fits in the lower panel. And since most of these are going to be falling on top of each other, we do see that the fits A do not really differ from one to the other, particularly in the smaller systems, as we basically drop our charged particle multiplicity density below 50. And B, the fit themselves actually turn out to be pretty horrible because, I mean, most of the time, I guess an accepted good value should be sitting at about less than 5. But for the PP system, we just basically don't get a good fit at all. So although we do have in the large systems somewhat of temperature splitting between the fits that the three fits, we don't really see that consistently falling to the smaller systems. So what we have to ask ourselves is whether or not this will change when we induce a strangeness canonical ensemble, namely having a strict conservation of strangeness into the fit, which was what we went ahead and performed next. And I went ahead and now, rather than showing the strange canonical ensemble on the right here by itself, I'm comparing it to the GCE that we just saw in the previous fit. So if you virtualize to the right, if you change your view to the right plot, what we do see once again in the same fashion as we plot for the GCE is that in the top panel, we do see a pretty definitive, I guess, splitting of the temperatures that are extracted when the chemical freeze-out temperature is set free between these the colors. So basically, we do see that the strangeness temperature is higher for all three systems with respect to the full fit with everything, and then more importantly, the light flavor fit. And the second thing that is worth noting here is that the actual independent goodness of fits that we do get in the lower panel of the right-hand plot, consistently, I would say most of the time will show you a better overall fit when you consider a flavor-specific fit into the thermal model than when you actually do not. So the blue and the red points are always going to be falling below or most of the time, except for maybe 1 or 2 of the points for the PlEd system, the PlEd system, sorry. But I mean, overall, the total goodness of fit is basically just going to be the addition of the blue and the red for the flavor specific fit, and it will consistently fall below the green, which will tell us that overall this is going to give us a better fit. And it does once again support the splitting of the temperatures that we had observed in the most central system, at least at a higher energy. So we do see that if we do want to see a good description of the data through the fits, the ensemble that we ought to choose ought to be the strangeness canonical ensemble. But we do, however, up until a certain point of charged particle multiplicity, we do see that there is still a deterioration of the full fit. And we do see that a temperature splitting creates an overall better quality of our fits throughout the light and through the strange fits. I think the next plot basically is just going to show this result in a different manner. I mean, these two plots are really not showing you anything different. On the left is just a one-to-one comparison of the two ensembles. And then on the left, on the right, I'm sorry, what I'm showing is this was just specifically I mean, we were just trying to come up with a better way of showing these two plots in one plot with respect to how the goodness of fit was differing. So basically in the top panel, what we're just going to be doing here is comparing the Grand Canonical ensemble goodness of fits values shown in cyan with respect to the values that we get from the strangeness canonical ensemble for the full fit. And then in the bottom, what we're showing is how it is that the chi-squares from the flavor specific fits differ from the chi-squares shown from the Grand Canonical ensemble once we use the strangeness canonical ensemble. So the bottom panel is just basically going to be showing you the goodness of fit difference between the full fit using an SCE with respect to the two flavor specific fits, once again showing an SCE. So basically what we want to see here in the difference plots is values that do not differ substantially from from the magenta plots in the top panel. But I mean, the information shown here is also shown in the previous plots. It's just a matter of actually, I guess, making the data a little bit more available in a single plot. So we do get the same result once again, just by looking at these. And I guess, you know, you might ask yourself, okay, so what big deal? You're able to do these plots. So what is it that you're really trying to do? Well, what we're actually trying to do is we're trying to replicate the data that was shown in this Nature paper by Elise, in which we do have an enhanced production of multi-strange hadrons and high multiplicity proton-proton collisions. And we do have a hadron to a pion yield ratios, which do show an increasing enhancement that differ with respect to their slope parameter as we start increasing in strangeness content. So we want to be able to do is replicate these yields using a thermal model using two temperatures across all three systems. And I mean, depending on what model you use to fit the data, it's not so consistent overall for all three systems. And we wanted to see if we'd able to actually be able to do this using the thermal model. So once again, I mean, this cartoon is the same from the previous analysis. So what we're going to do basically is assume the two temperatures that we extracted from an energy dependence analysis, namely the T sub L temperature as a light flavor freeze out at 150 mega electron volts. And this is the temperature that we're using in the thermal model to calculate the positive pion and the anti-proton yields. And then we're going to calculate the anti-hadron yields for the strange baryons as well. We went ahead and did it also as well for the phi meson. And we're going to fix that temperature for the thermal model 165 MeV. Then plot the anti-hadron yields, 2 pi plus yields, as was shown here. However, here was actually the sum of the two particle antiparticles, and then see how it is that the model performs. So before we go ahead and do this, it is worth noting once again that the volume itself was allowed to basically fluctuate as a function of dNCH d eta Otherwise, we wouldn't actually get a proper scaling. And we wanted to make sure that there is a proper scaling across the volume. So we see that in the three different panels on the plot, on the y-axis, we see the extracted volume from the thermal model. And then on the x-axis, again, as a function of charged particle multiplicity density, the top panel shows the volumes that are extracted by setting a freeze-out temperature of 150 MeV. The most bottom panel shows this for the strange temperature of 165 MeV. And then the middle panel just basically shows what we call the control volume, assuming once again, one single freeze-out temperature. And I mean, we do see that there's a difference in the volumes, particularly between the light flavored freeze-out temperature as well as the strange flavored freeze-out temperature, which ought to be expected as these two volumes are themselves corresponding to different times in the space-time evolution of the fireball. And basically what we went ahead and did was just put these temperature values into the model for the flavor-specific particles, and then we wanted to see what they will look like in this plot. So this is basically going to be what I would say is the end goal for the analysis, which is trying to describe the particle yield ratios at least using two temperatures. Once again, for the pions and the protons, this temperature was fixed at 150 MeV. And then for the lambda xi and omega antiparticles, we fixed it at 165 MeV and plot them with respect to the experimental values. And I mean, they do replicate the data pretty accurately up until values of charged particle multiplicity density below, I would say 10. We basically get an undercalculation of the yield. So this undercalculation of the yield is a little bit tricky to be able to replicate appropriately, because what winds up happening is that you are decreasing the volume onto which the hadrons or the strange baryons themselves are capable of being produced, while you're increasing the volume for the pions themselves. So basically you get a ratio into which you have the numerator dropping at a rate that is too large as the denominator is itself falling at these specific freeze-out temperatures. And this is what I would say fully determined by the volume. But overall, I would say that the data can itself be replicated pretty well, in which we actually do not allow the correlation volume to change. We also do not allow gamma sub S, which is going to be this strangeness saturation parameter that is usually associated with canonical suppression, as well as the rapidity window in our analysis is not changing. So this for me was one way to actually secure the only thing as being determined, the determinant of the yields being reproduced to be the temperature differences. And then, I mean, yeah, the next thing, which just a sort of like a fun phenomenological, I guess, exercise, which was trying to replicate the yield that we do see for the phi meson. And I mean, as we know, the phi meson is going to be rather tricky because it is an SS bar state. So in principle, one would, generally treat it as an S equal to 0 state. So what we do see in this plot here are three different treatments of strangeness content for the phi meson. In purple, we have the model calculations of what the yield ratios would look if we treat the phi meson as being an S equal to 0 state. And we do see that for the smaller systems, we do have an overcalculation of the phi to pi ratio, which, I mean, this is always going to be typically the case where there's an overcalculation. So the next thing, I mean, the thermal model itself is rather simplistic and doesn't really know itself what it is that these values should be. So one is pretty free to change them around. So I just wanted to see what would happen if I changed these values ad hoc to values of strangeness equal to 1 and strangeness equal to 2, and see how it is that the calculated values would change. And you do see in the cyan for strangeness equal to 1, while the yield ratios do improve, there's still a slight overcalculation in most of the smaller systems. And then if you push this further on, giving the phi meson strangeness constant of 2. The yield ratios also kind of increase, but once again, they're undercalculated and are substantially overcalculated. And this is just basically done in order to show, at least phenomenologically, that the best treatment for the phi meson in order to replicate the yield specifically for the thermal model is going to be a compromise between S equals to 1 and S equals to 2. But this is also, something that's, I would say, not substantially too well understood in the scope of the hadron resonance gas. But these were basically just the results for this. And yeah, this is going to be the end of the system size dependence. So, I mean, we just actually submitted this paper. So right now it's under review. So we'll see what arguments we get against it. But any suggestions or any comments are also always welcome. And so basically, I've shown you what has been done, and now I'm gonna just show you what I've been doing as of now and what is to be done with respect to the thermal model. So basically, the first thing was just doing a little bit of housekeeping with respect to the Elise fits that I performed. And something that should be a bit of a red flag or a trigger is that in this light flavor freeze-up that I was showing, we were actually using the kaons in the light flavor fit. So, immediately you should tell me, oh, okay, well, Fernando, this isn't okay because you're calling it a light flavor freeze-up and the kaons themselves are not going to be a light flavor particle. So, what can you tell me about that? So what I went ahead and did just to be able to let myself sleep at night was, rather than using the kaons in the light fit, I can go ahead and replace them with the deuteron yields that we have at Elise and see if the two temperatures that we calculate lie within themselves with respect to the goodness of fit. So now what we're going to have, instead of a pi kp fit, we're going to have a pi pd fit, and allows for us to have a true light particle fit to the yields and removes the need for the kaon to be present in all of the fits that we're performing. Although the kaon has been shown to be insensitive to the freeze-out temperature by other papers that have been shown, I just wanted to be able to do an in-house calculation of this by removing it from the fit and seeing what it is that is affected in the thermal fit by it. Obviously, there's going to be other considerations taken into account, namely that there's an increasing baryon number from the proton to the deuteron. And then we also have similar mass to some charged mesons like the D0, the D+. But these also bring interesting points to discuss in the latter parts of the phenomenological analysis that we're currently performing. So I'm just going to show you these results, but what I do want to guide your eyes to is basically just going to be the topmost line of the table into which we have this new pi pd fit, and the extracted freeze-out temperature we get from this is 145-ish mega electron volts with a goodness of fit, a reduced goodness of fit value of 1.36, sorry. And what I want to compare that to is a previous pi kp value that we would get, namely what the temperature looked like, as well as the goodness of fit. And we do see that the two temperatures themselves are well within their error bands, and also the goodness of fit for both of them is pretty much the same, while it's actually a little bit better for using the pi pd. So we can conclude that the inclusion of a pi pd fit instead of a pi kp fit improves the quality of the fit. It serves a good compromise between the fit quality and the flavor content. But this actually goes ahead and tells us that the pi kp fit is not that bad of a I guess, choice if you're limited with the number of statistics for your samples where you only have kaon yields instead of deuterons. So overall, this ad hoc cross-check as to whether or not the kaons themselves were sensitive to the temperature and vice versa turns out to be a little bit of a success. So this was just a matter of housekeeping. And then, yeah, so the latter part of this is going to be basically what I'm currently working on right now in Strasbourg with Professor Boris Hippolyte. And what we're going to try to do is basically expand what we had seen before, this zoo that only included light and strange hadrons, into actually including an extra quantum number of charm into the thermal model so that we can start replicating through the thermal model charmed hadron yields, which will take us further into heavier flavor. And I think that this is pretty much a topic of interest for most of us and will be a topic of interest for me in the coming years. So this is what we've done. So basically, we went ahead and added 80 additional states to this PDG 2016 plus list. And these are going to be now from the PDG 2020 list. I went ahead and included hypernuclei to these because this data is actually also available with respect to yields. And the mass cutoff right now is going to be at the lambda sub B, which sits at around 5.62 GeV. This was done specifically to include any resonances or any actual particles that have feed down contribution to the D mesons of all of the different flavors that we know, as well as the J psi. Now, as to whether or not charm statistical hadronization is possible is also a topic of contention, but it has been argued that these charmonia are going to be themselves implanted, or that charmonia themselves will be implanted into the quark gluon plasma. And we do have a modification observed in terms of sequential melting. The charmonia themselves are thought to be screened by the quark gluon plasma as the production occurs at the phase boundary, and they do signal a deconfinement for the charm quarks. This production, however, will be scaling as a function of collision energy, and then that makes it such that quantum quark production probability will be scaling with respect to the number of CC bar pairs squared. And this is done with a fugacity G sub C, which is similar to this gamma sub S factor that we had in the strange sector. So what I just wanted to show is a preliminary D0 yield calculation that we were able to do just as a cross-check to see whether or not the thermal model right now is capable of producing this using this gamma sub C factor that is determined by the charm balance function. So this is going to be obtained from measured charm cross sections at PP collision at 7 TeV, which is shown to be about 1 millibar. And once again, just to show you what the actual fit itself will look like. In this case, I didn't assume any flavor hierarchy of any type. We just wanted to see what the fit would look like. And what we do get is we get an extracted temperature, once again, that sits at the very, very famous temperature of 157 mega electron volts, into which we can replicate most of the experimental yields quite accurately. Once again, below 4 sigma for all of them. And then the D0 itself is basically implanted into the fit by this gamma sub C factor. So basically what the gamma sub C factor is a correction factor that's scaling to the power of the total number of charm quarks included in the particle that goes in the fit. And this is where we are now with the expansion of the list into the heavy flavor. I do have some additional in my backup slides, some additional predictions that we have for multi-charm baryons, but they're extremely preliminary, so I didn't really want to show them too much. But if you want to see them, I can go ahead and show them. And then, yeah, this is pretty much going to be where we're sitting around now. So just, you know, getting back to what it was that I showed, because I think I'm running out of time. I mean, in part one, what I wanted to basically share with y'all is that we do calculate the slide and strange fit at a vanishing baryo-chemical potential, namely that we do have two different temperatures of 150 MeV for the light flavor and of 165 MeV for the strange flavor. This corresponds to that same 15 mega electron volt difference that we had previously seen calculated from lattice QCD, as well as from other calculations using HRG yields and fluctuations. And I would say that, you know, this could confirm the existence of a flavor hierarchy extending down into the BES energies. They do depict consistently an overall better quality of the fit. And then once again, you know, with respect to what the physics of this might suggest, this convergence of the two lines at high mu D, you know, might tell us a little bit something about where this critical point may or may not be hiding. Now, in the second part, we were able to use the strangeness canonical ensemble using a 2-temperature chemical freeze-out approach to describe all three at least collision systems. And this was done without having to modify the rapidity window the correlation volume B sub C, and nor the actual strangeness saturation parameter. And we have to make somewhat of an interpretive approach to this. So what we can sort of suggest here is that for LHC energies, there seems to be a flavor separation prevailing in small systems. And the question that this might pose, at least in the scope of HRG, is if this is enough to be able to be one signature of QGP formation in smaller systems, though there are plenty of other questions that need to be addressed before this can become a definitive statement. And then the latter part of part two was basically just a phenomenological sort of game playing to see which would be the best way to describe phi meson production. And it does seem that there's a favoring of this concept between 1 and 2. And then this is what we're basically working on now, which is adding charm into the thermal model. And some of the questions, as I was saying, that can be exploited and taken into consideration is the similarity between charm hadrons and the deuteron. And we do have, as we have seen, at least experimentally, vast differences in particle production of these 3 particles here. So this might also tell us as to whether or not there's some type of enhancement for charm particles with respect to the others. Though once again, there are different considerations for the deuteron because of the fact that it does have an increase in baryon number. So for the SHM charm extension, we consider the scaling factor for gamma sub C to take the initial charm production into account and can be used for multi-charm yield predictions, this time with thermos, which we know has been already fully expanded. The list for thermos as well as the actual thermos code itself is now readily available to include charm. It might be still in the development branch on the kit, but this is something that Boris and I were able to get going in the past month, I would say. And other things that have been done with the thermal model that I haven't shown because they're not really part of my personal analyses will be using the hypernuclei into the strange fit in order to add more degrees of freedom into the actual fits themselves. Then also trying to expand a multiplicity-dependent 2-flavor chemical freeze-out campaign into the BES data, but we know we do have this non-trivial MUB dependence. And there are other students in the Houston group that are now using thermal model predictions for pentaquark production in small systems. And this is just basically the end of this. I mean, the rest of this is just to talk about some things that I was doing while performing the analyses, I mean, namely being in the LF strangeness group, but at least doing multi-strange baryon production in small systems, doing some electromagnetic calorimeter batch channel mapping as one of my service tasks, as well as the Gen 4 quality assurance. And Lauda already talked about me being junior rep while out at least, as well as being diversity office junior member, and the other tasks that I performed with the University of Physics department. But this is basically just to emphasize my interest in representing, I guess, the junior members of our community, which I believe, need adequate representation. As I would consider the junior members to be a minority group, not with respect to the total number of people, but just with respect to the representation that they may or may not have in the field. And then, these are my actual interests into things that I would like to promote in the next 3 years during the postdoc, which is promoting inclusive environments in STEM for underrepresented minorities, as well as promoting diverse workforces. And I mean, the rest is just things that I like to do in my spare time. But yeah, I think that sums up what I wanted to talk to y'all about.
Thanks, Fernando. Super interesting talk. Any more questions?
Yeah, I have a few questions, but maybe I'll let someone else go.
Let's see. Do we have any questions on Zoom from anybody on Zoom? I don't see any raised hands.
Okay, nice, Fernando. Your slide 19. Yeah, right. So here, or maybe the slide before. I can't really see the slide number from here. My eyes are pretty crappy. So what's going on in the Grand Canonical ensemble at the very low multiplicity? There seems to be this up and down jumpy behavior in the chi-squared. Seems to work, doesn't work. Seems to work, doesn't work.
I was only repeated.
Yeah, so exactly. I mean, this would be in PP, and I mean, overall, I would say that okay, there is a jumping, but in principle, I mean, in the lower multiplicities, they would all be sitting at around the same value. I mean, it's sitting at around a 9-ish, maybe a little bit above a 9-ish. And to me, this is just telling me that it's not working.
No, but what's the point in the middle? So you're saying that is just PP?
The filled block is on PP. The
So
opening.
you're basically talking about going from PP to P-lead and from P-lead to PP. I mean, yeah, I would have to say that this is just going to be a mess in the manner in which basically.
Right. Okay, so I didn't quite see that from here. So, but on a more conceptual basis, if I have 3 particles in a D&D, at some point this should fail, right?
Wait, I'm sorry, can you repeat that?
So if I have like 2 or 3 particles in my, in my DN charge D8, a very small number, in principle, that is not representative of a canonical ensemble, right?
No, yeah, exactly. I mean, you're right about this because I mean, you basically don't have enough participants in your party to do anything.
Correct. So conceptually, why are we even trying to fit this less than some multiplicity? And is that boundary calculable?
So, okay, as to whether or not the boundary is calculable, I'm not sure I can give you a qualified answer for this, but as to the why, I mean, in principle, what I'm curious about is to see as to whether or not at least energies, the actual energy range that we're reaching makes it so that when you have a limited number of participants in your thermal model, in your volume that you're working with, whether or not this energy is enough to produce strange particles from the limited number of players that you have.
Okay.
And this can be tested, although the SHM is slightly, or actually it's not slightly limited, it's very limited in what it does, and it's fully assumption dependent. It can be still used as a tool to be able to provide, just a small little predictor for whether or not this might or may not be true.
Mm-hmm. So, okay, I mean, I have more questions, but anyone else?
Yeah, I guess I can ask a question here. I guess I was curious, like on the right, like your point was the temperature, that there's still now there's a temperature difference in the low multiplicity part, correct?
Yes.
Yeah, so I guess like how seriously should I be taking that? Just because I feel like, or like some of the fits are still not, like they're better, but they're still not, great, I guess. So like how seriously should I take the differences in that region with the SC?
Yeah, so I mean, I would have to say that anytime you see like I was saying before, a goodness of fit value below a 5, this is usually taken to be a pretty terrible fit, right? So under this, statement, as seriously as you may want to take it, I would say that these last 3 points in the smaller systems, the fits themselves may not actually be a bona fide representation, right? And then in principle, these three multiplicity bins, if we keep them in mind, these were actually the most troublesome bins to be able to fit in the latter parts of where we were having the calculated yields.
Okay, so Fernando, so this is not strictly on what you have showed, but what we can extend this to. So Star took a lot of data last run at 3.5 GeV fixed target and okay, I think 3.8 something fixed target and also collider. So which have different, different values of mu b that are hopefully on this scale, on your scale that's off the plot, where you mentioned they might overlap. So is there any a priori prediction that this can do, or is that something that is irrelevant until you have data?
No, so I mean, this is an excellent question because I'm going to go ahead and move to, I guess, in this plot, right? And what you would have to ask yourself is, okay, what is it that these calculations here would look like at lower energies, right? So with respect to the lower energies that we're having and what has been shown, and I actually don't show a plot for this, but there's a plot that actually, yeah, René showed a plot about this, where you show that, let's take the Xi, for example, because I think the Xi gives us the best, I guess, depiction of this. As you start increasing the energy, what winds up happening is that these calculated yields start stacking into one another. So they would look exactly like, what my model looks like with respect to the energy. And as you start lowering the temperature, there begins to be not splitting, but there begins to be spacing as a function of energy. But the actual spacing itself, I would say, as soon as you hit this, the 64.2 energy becomes basically non-apparent anymore. And what that tells me is that you reach a saturation of strangeness at some point in the actual energy realms that we're dealing with across the two colliders. So what this would tell me, at least with respect to what Elise is doing, is that at least energies, strangeness production is already fully saturated, meaning that everything that we see at Elise is fully enhanced with respect to strangeness. I mean, obviously, this is only with strangeness and can, in your mind, maybe perhaps be extrapolated into heavier flavor. But for this, then for sure, I would have to say that this is something that is dependent on more measurements, specifically in heavier flavor across multiplicities, because this
is the same logic for charm, right? This is the same logic you say for charm. Yeah,
I mean, in principle, yeah, you can extrapolate it for charm. Yeah. But for charm, I mean.
But then I'm confused again. Okay. All right. I'll let you answer and then I'll answer.
No. I mean, the thing is that, like, for charm, what you run into further complications using a different temperature approach, because you do have to hang on to this gamma sub c value, right? The gamma sub c value is going to be fully determined by the charm cross section, and that's going to be determined at least with respect to the PP sample, right? So, I mean, in principle, you can fix gamma sub c to a value, then allow your temperature to fluctuate. And then this might make it such that in the nice little space-time diagram, we could have potentially a third temperature that's associated with your charm, I guess, freeze out. But I think the first step, at least for me, is the strange favor freeze out. I mean, with respect to how the actual scaling of charm production occurs across different energies, I mean, I would assume that it's similar, but I also would assume that the effect is going to be significantly different.
Well, because at different energies, you have different types of recombination style effects, right? So if you go to the D0, I would expect if you include, for example, star data, let's do some hypothetical, make sure star data is there. I would expect to see a difference between the temperature that is, I mean, the D0 plot that we showed, the temperature sitting bang on top, that's like kind of scary, right? I would expect that to be very different at star energy, no?
Wait, I'm sorry, which plot?
I think it's when you did the D0 fit,
Yeah,
at the very end,
yeah.
where you had it was the last point.
Here.
There, yeah.
Yeah, so I mean, this one is, you're talking about why it's sitting right on 0.
Yeah.
Yeah, I mean, in principle, it's right on zero because it's the only charm degree of freedom that we have here, right? So it's fully determining gamma sub c. So of course it's going to be falling right here. I mean, so let me show you what, actually no, because we don't have the model over data, but this is what we have for this. I mean, this is what happens when you still implement, so we can do this for the entire zoo, right? I mean, some of these baryons, we have no experimental data. And then what I have to ask myself is, okay, well, let me there go gamma sub c and gamma and the temperature, let it run free and then see how the yield's different. And clearly a difference in temperatures is going to give you a huge difference in the production. And then we can even do so for the upsilon, and the upsilon is behaving ridiculously, right?
That's very cool. Yeah. Okay. So this is nice to see. Mhm.
Yeah, exactly. I mean, the only thing is that like we do have this fluctuating gamma sub c value, and the gamma sub c value tends to be very dependent on the production cross section for charm. So having this change is telling you that you have a changing cross section as you basically increase the temperature, and it becomes a game of trying to figure out what is actually changing and what is not, or if this is just a statistical mishappening, you know?
Mhm.
But in principle, into this fit, there is readily available data for D plus, D sub S, and the lambda C, but I'm not sure it's public. So showing these is not something that one can do, you know, pretty freely. But it would make the fit better, and I mean, it would also make it so that this point doesn't sit here, because this is fully determining what this gamma sub C value will be.
Yeah. Nice. Okay.
So I guess that was one of my questions. Are you planning the thing about the temperature for the charm? Are you when you pursue the charm part, are you going to try to extract a third temperature? Is that the goal, like to then do a third fit for charm particles and sorry, yeah, for charm particles, and is that?
I mean, this is actually the goal in mind, you know, because then it would really truly be a flavor hierarchy and not just the strangeness sequential freeze out, right?
Yeah, that's cool. I guess we should maybe be able to do something like that in run 3 analysis. Yeah, maybe like get some more charm states and then right.
Yeah, no, exactly, and this is something that's fairly interesting because I mean, being able to get multiplicity dependent analyses at least, it might not be too trivial, but maybe getting them across other experiments. I mean, there are other experiments at CERN that already have the data available, but the multiplicity dependence analysis hasn't been done. So just being able to push interest into actually having a multiplicity dependent analysis. I mean, this would make it so that A, we can mix a bunch of systems about extracting temperatures, and then B, also go about through to the actual huge energy realm that we have, because I mean, there's still not like a nice little, I guess, seamless form of analysis across all the experiments, and it would be nice just with respect to seeing how powerful and far-reaching the thermal model might be, because it's extremely simplistic, right?
Yeah, that's cool.
Now I have a follow-up question, I guess, to your last statement. Maybe I'm trying to not sound too critical, but I'm usually quite, if I'm honest, I'm quite critical of the statistical hadronization model, I guess. So it is strong in a simple way to predict the integrated yields, right? In lead at least. So what do you think, in your opinion, like over the next few years, like what makes it worthwhile to study the SHM instead of studying another model that is actually dynamical and can predict also stuff like energy loss, flow, and have actual PT spectra?
Yeah, I mean, this is a pretty loaded question, but I mean, since I mean, this was like a large part of what I was doing as a graduate student, and now that I'm getting toward the end of it, you know, I'm not too offended with somebody telling me that the thermal model might have reached its limit. I mean, it might just be that at some point in the near future, the thermal model just becomes a cross check, but I mean, what I would want to say is that this is something that anybody can do. And it's a nice little cross check to just be able to see whether or not these dynamical models themselves are consistent with what it is that the statistical calculation will give us.
But what about the event generator mode? Maybe that's where I can see this being more practical, like instead of just a cross check, take all this physics that you technically learned from here with the temperature dependence, throw it into a generator. Is that, I mean, you had one word on it at the very beginning, but you didn't have time to come back to it.
Yeah, no, so I mean, the event generator itself can be used also, but I mean, if you compare it with other event generators that you can use on the grid, since FIST does have a built-in GUI, it takes so long, and the computer sometimes sounds like it's about to take off into space. So I mean, it does what every other event generator will do, but the thing is that like you can in principle use the event generator to reproduce the events based upon the extracted freeze-out temperature or the parameters that you're using. I mean, I think the main thing to do, not just with FIST, but also with Thermis, which may not be a trivial finding, is being able to actually draw contour maps with respect to the sigmas drawn by the chemical freeze-out temperatures as well as the volumes, and show that when you plot, let's say, T versus V, and then you show these contours, if the contours themselves are separated, when you're going across three flavors, I mean, this becomes a further check that this flavor separation is not just caused by independent fits, but it's actually based upon how well the data is being fit to the HRG.
Yeah.
Because I mean, at the end of the day, we want to be able to replicate the data somehow, and we want to be able to do it in the simplest manner. And this is as simple as it gets. I mean, sure, we have some fundamental assumptions, but I mean, it's not as crazy as some other assumptions that you may get from something more complicated. I mean, in principle, I think that there are people now using hydrodynamical models into which they themselves can actually start turning different points into where you have specific flavor-dependent volumes in the evolution of the fireball, and they themselves can basically make it so that the findings that we have here can also be correlated to findings that they find in hydro. So I guess, I don't know, to answer your question, Mike, this just becomes basically a way to stir a pot and see if stirring the pot makes it so that enough people just in their spare time try to see whether or not this can be replicated with other methods. Rather than just, you know, taking a single freeze-out temperature as a stated fact just because that's the way that it's always been done.
Yeah, I guess it would be nice to see if you include indeed very different hadrons with different quark content, so that they somehow group together depending on their constituents, right? Because that indeed gives you a certain belief that you would have different freeze-out temperatures, chemical freeze-out. Because, yeah, it's also true that, so in one of your first slides, when you said you add a second layer for the strangeness freeze-out, if you add additional freedoms, degrees of freedoms to your model, then of course they're going to be different, right? Because you just want to fit your data, so they are going to. I mean,
yeah, exactly. It no longer becomes a fit; it's just a road calculation. And I mean, then yeah, this becomes a problem because as you start adding more and more free parameters, then your number of degrees of freedom starts basically dropping to nothing. And then with that, I mean, you can't get a bona fide chi-square out of that because your degrees of freedom are pretty much zero or or negative, you know, whatever that might mean.
We've come a long way from some of our older generation standing up at quark method and saying that everything we need to know is in this statistical hadronization model.
Yeah, exactly. Yeah,
We have come a long way.
Yeah, I also like the attitude of Fernando towards this, because there are some people that treat it as the holy grail, right? And maybe it's not. But in what it does, it's really strong. If you take such a simple model and it gives such a good prediction like that.
It has to break at some point.
Yeah, well, yeah, but it can't. Yeah, but if you ask what the expect,
we won't know where it breaks until we break it.
Yeah. Come here and break it, Fernando.
I'm trying.
I think we're transitioned into chatting now.
Yeah, I was about to say, any more questions? Anybody on this, in the void? No. Okay, so let's thank Fernando again.